All right, so here we got this question where you got the vector function here and the curve and so forth, and then the limits. You can read the question. I only got 5 minutes. The trick is when you're doing these vector integrals, it's a mix and match situation. Each theorem case has like 3 to 5 different situations that you choose from. You need to know what method to choose. And if you're on an exam, if you write the correct method, the correct matching formula, that's like half credit. And then if you convert it properly, that's like 40% more credit. And then the rest of it's just arithmetic. Basic calculus is worth hardly nothing. So you want to make sure you're neat and clear. So let me show you. This is a pretty long problem, but it's actually quite simple and quick once you get once you identify the right thing to use here. So read the question. Says to use Stoke's theorem. That's the first hint. So you're probably going to go find Stoke's theorem, right? So here's Stoke's theorem. But this theorem right here is not necessarily going to work for us. It could, but it may be difficult. I won't go into that. Again, they only give you like 5 minutes on here. So first thing I do is let's just, we take the curl of f here and we identify the surface and so forth. I did a little 3-dimensional graph here so you could see we've got this plane in the xy, in the first octant in the xy plane. This diagonal planes over a surface, so we got a little 3-dimensional object going on there. I identified the limits here. The limits may change depending on how we set it up. That's and when you're doing these questions, you want to be on the test step by step. Be very neat, be very clear. A lot of people lose points for not just writing clearly. So the first thing I did is the curl. That's easy computation. I'm not going to go through that. Then we need to identify the correct formula to use, because there's many formulas, and depending on what you're working on, that's going to all change. So if I go back to this picture here, you see how this is a smooth surface and it's over this looks like a rectangle, but it's actually curved. It's a curved surface. Well, that you could easily use this original formula for. However, we have a sharp domain area, piecewise sections. They're smooth curves, but they're piecewise because they're sharp. They're not differentiable where they connect because they have a sharp point. That's the rectangular base. If you look here, we have a rectangular base with this plane going over it. So in the XY plane, there's this plane that is projected over this thing. And this is the surface that we're going to integrate over this rectangular area. Drawing it can help, so forth, whatnot, but whatever. Let me just go through the formula because I'm already halfway through the time. So this is because we have the sharp angles over that and we have a flat surface, we're going to use the formula with the normal vector, the unit normal vector. Okay, unit normal vector. So I get the curl, then I find the unit normal vector of that surface. Well, that surface is a plane. So you take the equation of the plane and the coefficients from ax plus bx plus cz equals d. That's your normal vector. Then you unitize it by dividing by the magnitude of the normal vector. That's your normal vector. Then you take the dot product of the two of them. Okay, so curl f dot the normal vector, and that gives you this. Now you take that. Now you have to find s, the surface. The surface is a formula right here that you just plug in the partial derivatives of that function that you found, of the original function of the surface here, this is the original function of that plane surface that is going over there, right there. You plug that into the ds part, and then that converts you into dA. And then now you take your dA and you put it into the formula with the dot product of the normal vector and the curl. And then you find your limits. Go back. We're integrating over this. X goes from 0 to 3. Y goes from 0 to 4. You might have, a function. It might be an iterated integral, which means you have a function in there. Then you plug it in there and you do the computation, and bada bing, bada boom. It's a very basic double integral from second year calculus. Very simple. All of these questions are usually quite simple. So on the exam, what you would have done is you would have identified the question. You would have then written this first. See how I numbered these? Then you would have done the computation and identified everything nice and neat in order, 4, 5, 6. That would make the teacher so happy when they grade it, or the TA, because it's nice and neat and organized. And then you get down here, you could just leave it right here. It doesn't say simplify in the question. This is just, can you get to this point is the big question, okay? So that's it. Thanks.